Hello and welcome. We are going to look at the Gram-Schmidt orthogonalization process. So we know that working with orthogonal vectors has its conveniences, specifically because the dot product between any two orthogonal vectors is 0. And that becomes incredibly useful because zeros obviously cancel out quite well. So let's suppose we have some sort of basis and we have that basis that spans some sort of region. And for instance, let's say I have I'll just draw kind of a plane-like shape here. And inside of this plane, I have two vectors that span that entire plane. And we see that there are infinitely many vectors inside of this plane. So one thing that would make sense is if I could either rotate one or both of them so that they're still both on the plane. So for instance, if I rotate this guy just enough, then I can form it to be perpendicular to my original vector. So I can get a 90 degree here. Remember, this plane is infinite, it goes on forever in all directions. But if I rotate it still within the plane, then I can make these two vectors perpendicular to one another and still have them span the same plane. So the basic idea here is that we take a basis and project one vector onto each other, thereby ensuring that the vectors become orthogonal. Finally, the vectors are normalized so that the set is a set of orthonormal vectors, which is very convenient. And let's develop some intuition before we introduce how this process works. So here we have two vectors, 2, 0, 3, and 1, 0, 6. So if we think about this as the x, y, and z axes, then the vector 2, 0, 3 is located 2 units this way, 0 units in the y direction, and 3 units up. So it'll look roughly something like this. Of course, we have to account for the fact that we're looking at this in a different perception. 1, 2, 3. So this vector will actually appear to be a little bit higher just because it's coming closer towards us, but nonetheless it's in the xz plane, right? And so 1, 0, 6 is as well. 1, 0, 6 is going to be somewhere up here, also in that plane, and we see that together they span the xz plane. Okay, now can you find two different vectors that are both orthogonal and span the same space? Well, absolutely. The most simple vectors that I can think of are the vectors, the one that is perfectly along the x-axis here, and then one that goes up on the z-axis right here. Can't get that to form. There we go. And so basically what we have is inside of this plane, let me just draw this as if we were looking at it in this direction. So what we would be seeing is the sheet of paper. And here are our two original vectors that we drew. And so if we form two vectors such that we basically just make this be the unit vector, and this is again our x and our z here, and a unit vector here, then clearly those two vectors still allow you to get anywhere along that plane that you want. And those two vectors, if they were unit vectors, would be 1, 0, 0. That would be this guy here, because that would point 1 unit in the x direction, 0 in the y, 0 in the z. And then this vector here, 0, 1, 0. Those would be two possible vectors that would make those perpendicular. Now, of course, I don't have to rotate both of them. I could just rotate one of them. I could rotate, for example, another possibility would be to rotate this one down and make them perpendicular like this, and that would work as well. And the Gram-Schmidt process really focuses on leaving the first one the same and then rotating all the other ones to get them to span the same space, to be the basis for the same space, to allow you to travel anywhere in that space. These are all analogous sayings that I'm using here. And the Gram-Schmidt process kind of works like this. So it works with projections. So now let's look at these two vectors that I have here. So I have x1, so I have some vector x1 right here, and ignore the v parts for the moment. And I have another vector x2 that comes from the origin and points to that point right there. Now clearly x1 which is this vector, and x2, which is this vector, are not currently orthogonal. So what I would like to do is I would like to rotate this vector so that it is orthogonal to x1. Now the way I'll do that is by looking at this from the projection standpoint. So here I can complete a triangle. I know that this guy right here is going to be some multiple of the x1 vector. So some multiple of the x1 vector, c1, x1, will give me exactly this vector here, that is this piece. And now I can write an equation because I really want this vector, which notice is still inside of that plane, but it would be perpendicular to x1. So what I'm going to do is I'm going to write this as an expression. I see that this here is x2, and this vector right here is some vector z. And what we know is that if we sum together c1 x1 plus z, that is going to equal, I'm sorry, I wrote x squared down here. That is going to equal x2. So adding tip to tail will put us at x2. Now, z is going to be the vector, the second vector in our new rotated basis. So let's refer to this as, actually, let's call that v2. That's going to be the perpendicular component of x2. So instead of using z here, I suppose it'd be better to say, let's call that vector v2. So v2 is what I want. In terms of x2, v2 is going to be x2 minus c1 x1. Now x1 and x2 are not perpendicular, but what I do know is that if I do that, c1 x1 and v2 are going to be orthogonal. So c1 x1 is orthogonal to v2. And therefore, what I'm allowed to write is, I probably shouldn't have written this quite yet. What I should have written right up here is that to find this coefficient, recall that the way we get that is by taking the, from an earlier lesson on orthogonality, as long as x1 and v2 are orthogonal to one another, then the c1 component, c1, is going to equal this vector over here, x2 dotted with x1 divided by x1 dotted with x1. And the way we solved that is we would have multiplied both sides by x1. And so if we multiply both sides by x1, then x1 dotted with v2 is 0. Here we get c1 x1 dotted with x1 is equal to x1 dotted with x2, which is the same thing as x2 dotted with x1. And then now to solve for c1, because a dot product is a scalar, we could divide both sides by x1 dotted with x1, and we get that coefficient there. So this new vector, v2, is going to equal that is going to equal, now that I have c1, it's going to equal x2 minus x2 dotted with x1 divided by x1 dotted with x1 multiplied or scaled to the x1 vector. Now the x1 vector, I'm going to leave that untouched. So this is where v1 comes in. So v1, when we're using the v's, those are the new vectors as part of our basis that is now orthogonal. So we said that we don't have to rotate both of the vectors. We're really probably just going to rotate one of them. So think about this one as x1, and that is going to be our new vector as part of our orthogonal basis. We're going to refer to that as v1. This guy here was x2. x2 is going to get rotated into v2. And so we're just going to relabel all the vectors, even though some of them don't get relabeled. So we're going to say that v2 is equal to x2, take away the orthogonal component, x2, oh, I'm sorry, I wanted to use, yeah, that's right, dotted with x1 divided by x1 dotted with x1 multiplied by, now since x1 is not going to get changed, but we're referring to it as v1, we'll just put a v1 there. And so this tells us how to get the second vector in terms of the first vector. Of course, we could have, we could be an n-dimensional space, so we want, maybe we have 10 vectors that span all of 10 dimensions, and we want to rotate 9 of them to make them perpendicular to one another and to the first. So if we continue repeating this process by subtracting off vertical components and dealing with projections, here is our, now I'm using the transpose operator, but, and here I used x1, but we called that v1. So I should replace all the x1s with v1s, just so it looks like the formula. So v1, v1, v1 there. x2 doesn't get changed yet because x2, this is the way we're going to convert it into the vector that is perpendicular. So for v1 is just going to get assigned x1. I'm not going to change the first vector. The second one, we're going to rotate it so that it becomes perpendicular, it becomes v2. The third vector, now from x3, we have to subtract off the 2 perpendicular components in the same type of logic that we used up here. If we think about x3, well, x3 is going to be the sum of 3 perpendicular vectors, c1, v1, plus c2, v2, plus c3, plus x3, plus c3, v3, or just v3. And now when I rearrange this, now these are all perpendicular, so I could generate x3 by using c1 and writing it as x3 v1 divided by v1 dotted with v1, and c2 I could replace that with x3 dotted with v2 divided by v2 dotted with v2, and then move things over to solve for v3, I would get this expression here. And this all goes back to the notions of orthogonality, and we would repeat this process indefinitely for the remaining vectors. And in general, to get the kth vectors, assuming that we have 10 of them or 20 of them, then in general it's just going to be a matter of taking, to get vk, we're going to take that new rotated vector of xk, we're going to take xk, we're going to subtract off all the orthogonal components, xk dotted with v1 times v1, xk dotted with v2, multiplied by v2, etc., up until we get to the k minus 1 vector. We see that we always stop at 1 unit short of our current vector. Of key importance here is that we do not need to have a basis for the entire space that we are in. So, for instance, if we're in 10 dimensions, then we don't have to have 10 vectors per se. We could only maybe span some part of 10 dimensions. We could be dealing with only, say, 3 basis vectors in R10, so maybe we can only go in 3 different directions, but we can still orthogonalize those 3 vectors. So here we have an example. Let W, that's the subspace, spanned by these 2 vectors. Clearly, I can't get to anywhere in R3 because I only have 2 vectors in 3 dimensions. I would need 3 linearly independent vectors to span all of R3. But so we say that x1 and x2, they span the subspace of R3. So to figure out how to rotate these, so again, I'm just going to write this as the subspace of R3. So we notice that with 2 vectors, we can only span a plane, and the plane that we had in our initial example was the xz plane in particular. Because the y components were 0, it was easier to visualize. So to actually visualize this plane is going to be a tad more difficult. So we're not even going to try. But to do this process, the Gram-Schmidt process says take v1 and just assign it to x1, or assign x1 to it. So we're going to leave the first vector unchanged because we don't want to do more work than we have to. We don't need to rotate all the vectors, just rotate the other ones relative to the first. So v2 is going to equal the x2 minus vector, or x2 vector, minus x2, not x squared, dotted with v1 divided by v1 dotted with v1 multiplied by v1. And so that's just consistent with our formula here. Take the current x vector, which is this guy here, and then v1, 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 and then the next terms, if we had more vectors, we would for v3 have x3 v2, v2 over v2 dotted with v2 times v2, etc. We only have two vectors here, so we'll have to do this 2 times. So we have the 1, 2, 2 vector minus x2 dotted with v1. So x2, really it's the transpose of it, dotted with v1. But we said that we can avoid using the transpose operator when we're dealing with dot products. v1 dotted with v1 will be 360 dotted with 360 multiplied by v1, which is 360. So this gives us the 1, 2, 2 vector. Here we'll get, let's see, 3 times 1, so that's 3, plus 12 is 15. So we'll have minus 15 over, this will give us 9 plus 36 is 45 times the 360 vector. And so now we need to evaluate that, see what that comes out to. And this will give us 1, 2, 2, this is equal to 1/3. So we'll have 1, 2, 2, 1/3 of 3 is 1, 1/3 of 6 is 2, 1/3 of 0 is 0. And this gives me the vector 0, 0, 2. And that's what my v2 is going to be. So v2 equals the vector 0, 0, 2. So now I have v1 and v2, and hopefully we can see that these, it's going to be hard to see that they span the same space. We're going to have to just trust the mathematics we did, but we can check orthogonality. And the way we would do that is just to take the dot product between 360 and 0, 0, 2, and you can see that we're going to have a lot of multiplications by 0, which tells me, in fact, that these two vectors are orthogonal. Now, one of the last things that typically takes place in the Gram-Schmidt process is to normalize the vectors, because working with unit vectors is so much more convenient. So v1, if we take, we can call this u1, so we'll take v1 and divide it by its magnitude. v1 is the 360 vector. If we square, we have 9 plus 36 is 45. So if we take v1 and multiply it by 1/45, which is 360, so we'll have 3/45, 6/45, and 0. This is now a unit vector. And u2, if we take the second vector and its length is the square root of 2, so if we take 1 over square root of 2 times the v2 vector, we'll get 0, 0, 2 over the square root of 2. Of course, you see this process can become pretty tedious for large vectors like we have here. So in this case, we would kind of repeat the same thing. You pick your starting vector. There's not a unique process. Like you could say v1 is 2, 1, 0, 1. It wouldn't really matter. But usually, just pick the first vector. So don't change one vector, leave it alone, doesn't matter which one, and then let's rotate the rest. So v2 is going to be x2, take away the orthogonal component, x2 dotted with v1 over v1 dotted with v1 times v1. And let's see if we can do this. So x2 is going to be the -2, 4, 0, 0 vector. When I dot x2 and v1, so that's these two dotted together, I'm going to get -2 plus 12 is 10. So this will give me -10 over v1 dotted with v1. That's going to give me 1 squared plus 9, or 1 squared plus 3 squared plus 2 squared, which is 1 plus 9 plus 4 is 14, times v1, which is the 1, 3, 2, 0 vector. And that would give me negative 10/14 is, let's see, divide by 2 would be 5/7. So if I take negative 2 5/7 times 1, so minus 5/7. 4 minus 5/7 times 3, that'll be 15/7. And then 0 minus, this will be 10/7, which will be just negative 10/7. And then when we evaluate this, we should have, let's see, negative 14, negative 19/7. And here we'll have, that will be 28/7 minus 15/7 is 13/7, and negative 10/7. So you can see these vectors can get pretty ugly. And now we really should divide this by its magnitude. And I think I forgot a component, and then 0 down here as well. And 0 right there. So you can just double check that these are going to, if I take the dot product between v1 and v2, they should now be 0. So I'll have 1 times negative 19/7 plus 3 times 13/7 plus 2 times negative 10/7 plus 0 times 0, but that's going to be 0. So we have negative 19, here we have 39, here we have negative 20. So we have negative 29 plus 39 is 0, and that does in fact work out. V3 would be the same process. V3 would just require us to get V3, we now take x3, take away x3 dotted with v1, over v1 dotted with v1 times v1 minus x3 dotted with v2 over v2 dotted with v2 times v2. And this should give us these coefficients here. 5/14 is what this comes out to. x3 v2 is negative 25/7. v2 dotted with v2 is 90/7. And then when we evaluate this and get our vector, we get v3 equals this guy here. And so now we have our set of v1, v2, and v3. And just recall that v1 was the same thing as x1. So that was the 1, 3, 2, 0 vector. So this was 1, 3, 2, 0. The second vector that we achieved was v2, which was negative 19, 13, negative 10. Negative 19, 13, negative 10, and these were all sevenths. And this was 0. And then our third vector that we just obtained was 8/9, 4/9, negative 10/9, and 1. And we should be able to just check that v1 is orthogonal to v2 is orthogonal, and v1 is orthogonal to v3, and v2 is also orthogonal to v3. And that's the Gram-Schmidt process.